Good morning, good afternoon, good evening, everyone. Welcome to ICANX Talks. My name is Lan Fu. I'm a professor in physics from the Australian National University. Today is our last talk of the April after a series of excellent talks in this month. Today we have Professor Kylie Catchpolet from Australian National University to presenting us the 137 ICANX talks. And joining us tonight also we have panelists, Professor Annalisa Bruno from Nanyang Technological University, Professor Fan Wang from Beihang University, and Zhongyang Ren from Peking University. First, let me introduce our speaker tonight, Professor Kylie Catchpolet from Australian National University. Kylie is a professor in the School of Engineering at Australian National University. She has research interests in solar cells and solar fields, as well as the broader energy transition. Her group has achieved world-leading efficiencies for perovskite and perovskite silicon tandem solar cells. And their work on direct solar to hydrogen generation was listed as one of the top 10 innovations globally by the Innovation for a Cool Earth Forum in 2020. She was awarded the inaugural John Booker Medal for Engineering Science from the Australian Academy of Science for her work on increasing light absorption in solar cells using nanophotonics. In 2022, she was elected as the Fellow of the Australian Academy of Technological Science and Engineering and as a Fellow of the Royal Society of Chemistry. So welcome, Kylie. The floor is yours.
Thank you very much, Lan Fu, for the very kind introduction. So I'll just share my screen. Okay, now, there we go. So the title of my talk is High Efficiency Perovskite Silicon Tandems for Electricity and Hydrogen. And the International Energy Agency said 2 years ago that the world has a viable pathway to building a global energy sector with net zero emissions in 2050, but it is narrow and requires an unprecedented transformation of how energy is produced, transported, and used globally. And there are important consequences of that. It means if we want to get there, we need from today no investment in new fossil fuel supply projects. We need by 2035 no sales of new internal combustion engine passenger cars. And by 2040, we need the global electricity sector to have already reached net zero emissions. So this is a challenge. And it's important to understand the scale of the challenge. We're talking about terawatts of energy that have to be supplied. And we're not used to normally talking about terawatts as a unit of power. Of course, a watt is something that might power a laptop. A kilowatt is something that might power a toaster. Megawatts, you're talking about small aeroplanes. Gigawatts, you're talking about a power station. But we need, and a terawatt, of course, is 1,000 times more than that. And we need tens or hundreds of terawatts for the world's energy supply. If you look at where that energy could come from, we need to have a look at the renewable resources that are available to the world. And what stands out above all is solar energy, because there's 600 terawatts available that's coming onto the Earth. And so that's the clear front runner in terms of the energy supply available. But there are other important contributors, and wind, of course, is going to be an important contributor as well. Just to get a scale of how much area you might use, Australia, of course, is where I'm from, and we have a lot of sunshine in Australia, but there's a lot of sunshine in many places around the world. But the little red dot there shows you the area of Australia that we would require to supply all of Australia's electricity, and the large green dot shows you the area that could supply the entire world's electricity. Of course, it's not all going to come from Australia, but you can see it's only a small area in terms of the surface area of the Earth that we would need to cover with solar panels to produce all our electricity. And in fact, we're currently undergoing a revolution in the type of energy that's being installed. So this graph shows you the global net new capacity per year. It's what we're installing every year in terms of power for different energy technologies. And you can see that way out in front is solar photovoltaics. So that's the largest new energy that's being installed globally. And second place is wind, and in much lower places are the fossil fuels. So the overwhelming majority, around 80% of the new capacity that we're installing globally each year is now renewable. So these renewables will certainly become our most important energy technology. Now, the main reason that these renewables are being installed now is that they're actually cheaper than the alternatives. Of course, all the policies are important too, but the renewable energies, solar and wind, are cheaper than fossil fuels, and especially if you take into account the risk associated with installing fossil fuels now, given the trend to net zero emissions. And this means that the energy transformation is in fact unstoppable because it's the cheapest thing to do. Even if you take into account the storage that you need, it's still cheaper than the alternative. So this graph shows you the cost for the renewables, but also the cost for the renewables with storage combined, and it's still cheaper than fossil fuels. And so again, this is what will be installed globally. This is what we're seeing installed globally at the moment. Now, photovoltaics, solar is a very big business now, and we need to take this into account in research. We need to understand what's actually required in industry. So the industry standard is silicon solar cells, of course, and they're typically produced at a rate of 1 cell per second. So very rapid production rate of cells, and a typical new factory will produce a gigawatt in a year, so about 600,000 modules per year. And it's highly automated and very efficient process these days. And of course, for those of us in research, we have to keep this in mind when we think of the processes that we'll introduce. When we think of new ways to improve the solar cells, we have to think it should be compatible with these kinds of production rates, and much larger, of course, as we transition towards more renewables. So you can see here what's happened over recent decades. This is a log scale plot of the photovoltaics that's been installed each year starting around 1980. And you can see that we have a more or less straight line over the recent decades that has been growing at around 38% per year. So that's an enormous growth rate, and it shows you why solar appears to have come from nothing over recent years. It's just been growing so fast. So even 10 years or so ago, we were installing around 10 gigawatts per year, and now we're installing over 100 gigawatts per year. So that's an amazing transformation. And of course, then you get a factor of 10 more than that, and then you're talking about terawatts. So looking forward, this is what's expected to happen. So this graph is from the International Technology Roadmap for Photovoltaics, and it shows you what's expected in terms of shipments per year. You can see now we're around about the 100 gigawatts, and expected by 2025 we're more like 200 by the time that we get to something like 2040 or 2045, we're expected 1,000 gigawatts, so a terawatt. And on the right axis of the graph is the global installation. And you can see by 2050, they expect a total installation of around 20 terawatts. So that's really making a significant contribution to the world's energy supply at that point. Now, there are a lot of important implications about the growth and cost reductions of solar that we've seen. It's not only about what we normally or what we've previously used for electricity. Of course, electric cars are cheaper to run than petrol cars. They can now be cheaper using renewable electricity. Similarly, in terms of heating for buildings, reverse cycle air conditioning or heat pumps are cheaper than gas, and they can be cheaper with renewable electricity. So this will significantly disrupt the oil and gas industries, which we've previously used for passenger cars and for heating of buildings. If we look at the entire world's energy sector, of course, it's not only about power. This is where emissions come from, where energy-related emissions come from. And energy, of course, is the most important factor. It's around 70% of all emissions globally. So energy is the main game to fix. So the largest segment is power. So that's significant. Then there's transport and buildings, and of course a lot of transport will become electrified. A lot of building heating will become electrified, but there are some parts of the energy sector that are hard to decarbonize, and they are particularly heavy freight, so heavy vehicles, and also industry. And for those parts of the energy sector, we have to look for other options. Our particularly prospective option here is hydrogen. So hydrogen can be produced from fossil fuels via thermochemical means, but it also can be produced from electricity via electrochemical means. And that means it's possible to be produced by renewable means. And once you've produced the hydrogen, you can use it for a range of things. You can use it for heating, you can convert it back to electricity, or you can use it for chemical reactions and feedstock. And so these are particularly promising for freight and for decarbonizing industry. So currently, hydrogen is typically produced by steam methane reforming. So it's produced from fossil fuels, and most of hydrogen is produced from fossil fuels, in fact. And so we need to, there's only around 4% or so produced from electrolysis. So we need to completely change that around if we want hydrogen to be a green and renewable fuel. If you look at what it would take to do that, the electricity cost is actually really important. So this is a graph of the cost of hydrogen as a function of the conversion efficiency of the electrolyzer. And electrolyzers are normally 50 to 70% efficient, and also as a function of the electricity cost. And what you can see is that if you can get the electricity cost low enough, then production of hydrogen can be profitable. So decreasing the cost of solar further is important for a couple of reasons. It's important because solar is going to be one of the major contributors to electricity across the world. And it's also important because decreasing the cost of solar means that producing fuels and chemicals from electricity could become viable. So once you have hydrogen, you can use it for transport. You can use it to convert back to electricity. You can use it as heat for industry or for buildings, and you can use it as a feedstock for chemicals and products. And some of those are particularly prospective, including heavy transport and also producing chemicals, which is difficult to do, and industry as well. Some of these are difficult to decarbonize in any other way. So we've seen that reducing the cost of solar further is very important. So in order to do that, we need to understand where the cost comes from. So if you look at the cost of a standard silicon module, you'll see that actually only 1/4 of the cost comes from, the 1/4 of the cost of a whole system comes from the cost of a module. So you can see in the picture there, we have 8 modules connected together and put on a house to form a system. So only 1/4 of the cost of that system is actually the modules. The rest of the cost is inverters, the mounting system, the cables, the cost of the people putting the system on the house, the interest rate. Those are called balance of systems cost, and they make up 3/4 of the cost of your whole solar system. Now, that means that having a higher efficiency can significantly reduce the cost. If you have a higher efficiency solar panel, you need less panels for a given system size, for a given system power. So it reduces the cost per watt of your installation, the mounting hardware, all of these balance of systems cost. So continuing to increase the efficiency of solar is very important for further reducing the costs. If we look at what cell technologies are currently in production, it's entirely silicon solar cells, largely the PERT TOPCon type cells, and that's predicted to continue in the future. And the role of TOPCon is important, we'll see in the slides later. The other thing that you can see starting to come in within the next 8 years or so is silicon-based tandems, and I'll be talking quite a lot about those today. If you look at the cell efficiencies over decades, you can see a general trend upwards. So this is the record cell efficiencies for a range of different types of solar cells made of different materials and made with different structures. Now, I said before that silicon cells are completely dominant in the market. And what you see is that for silicon cells, the efficiency curve is actually totally flat. It hasn't increased in around the last 20 years. And there's a very good reason for that, which is the fundamental physics of single junction solar cells. So silicon solar cells are very highly optimized, and the efficiency is actually limited by the fact that you have a single semiconductor which has one band gap. So when you have a single semiconductor with one band gap, what happens when the light comes in is that it excites an electron from the valence band to the conduction band. If the energy of the photon is higher than the band gap, then the electron will fall down to the edge of the conduction band, and you have that lattice thermalization loss. So that's number 2. If the energy of the photon is less than the band gap, of course, it doesn't get absorbed at all. So these two, 1 and 2, are the major loss mechanisms in solar cells. And the result of that is that there is a theoretical efficiency limit for single junction solar cells. So this is called the Shockley-Queisser limit, and it's for a silicon solar cell, because of its band gap, about 1.1 electron volts, the theoretical efficiency limit is around 29%. Now, if you include some extra physical factors of silicon, like Auger recombination, that brings it down to around 27%, and silicon solar cells are already 26% efficient. So there's really nowhere to go with the efficiency of silicon solar cells. So just visually, what happens then with a silicon solar cell is that it uses the red light, long wavelength light, efficiently, but the blue light that has extra energy in the photon is not used efficiently. All that extra energy that blue photons have is lost as heat, and overall that limits the efficiency of the solar cell. So what you can do instead is put a high bandgap material on top of your silicon solar cells. So this is the concept of a tandem solar cell. Then you have the light coming in, and those blue photons will be absorbed by the top cell, whereas the long wavelength light, the red photons, will go through to the high efficiency silicon solar cell. And overall, this way you can increase the efficiency through a higher voltage. So this shows you this in another way. And if you plot the theoretical efficiency you can see that you can get to some very high efficiencies. The maximum efficiency for a 2-junction tandem, so 2 cells, is 47%. That's the theoretical efficiency. The other thing you can see by looking at this graph is that silicon with a band gap of 1.1 electron volts is actually very good as a bottom cell. It's nearly ideal. And that if you have a top cell with a band gap between about 1.65 and 1.75 electron volts, then you're in that region where you can potentially get very high efficiencies. Now, people have tried to make silicon tandem cells with the 3,5 semiconductors, for example, a gallium arsenide or gallium indium phosphide semiconductors, and you can get very high efficiencies there, over 30%, but those materials are very expensive, much too expensive to use on Earth. They're good for things like satellites, put them in space where you don't really care about the cost, but for solar cells that we use on Earth for our energy, they're much too expensive. So we need to use cheaper materials for the top cell. So a very promising class of material for the top cell are the perovskite solar cells. So they've just emerged in the last 10 years or so, and you can see that the cell efficiency has climbed very rapidly for perovskite solar cells. Perovskites are a class of materials, so it's not a particular material, it's actually a class of materials with a common crystal structure. So that's illustrated there. You can see the classic octahedral crystal structure there. So this was originally found in 1838 as calcium titanate, which also has a perovskite crystal structure, by Lev Perovsky, who was a Russian mineralogist. For solar cells, the organometal halide perovskites are the materials that we use. So you generally have an organic cation together with other cations, cesium, rubidium. You have the metal, which can be lead or tin, and then you have the halide, iodide, bromide, or chloride. Some of the special things about perovskites is that they have a high absorption coefficient because they're direct bandgap materials. They have long carrier diffusion lengths and high intrinsic defect tolerance. That's something that's very special about the perovskites, is that they're really not very sensitive to defects. And so you have very good electronic quality, even if you have quite a defective material. And another important point is that you can change the bandgap of the perovskite material by changing the elements that are in the perovskite crystal, and that makes it very prospective for a multi-junction tandem solar cell. Another important point about the halide perovskites is that they're very easy to process. So you can spin coat them, you can print them, and all of this makes them easy and cheap to use. So importantly, they're low cost. You can deposit them by a range of different techniques. So in the lab, we usually use spin coating, but it's also possible to use blade coating, to use co-evaporation of the precursors. You can use co-evaporation together with chemical vapor deposition, or together with blade coating in a two-step type process. And overall, by doing this, you can get to potentially low costs that are comparable, or sometimes, by some estimates, significantly less than silicon. So this means that perovskites can be both highly efficient and low cost, making them very prospective for tandems. Now, I've said that we need high efficiency for perovskites. So when we're looking at how we might build a perovskite tandem cell, the first thing that we need to think about is, how do we make the high efficiency perovskite solar cell? So this is some of the work that we started with. We were looking at passivating the interfaces. Now, I said the perovskite itself is quite tolerant to defects, which is good. A lot of the loss in performance with perovskite cell occurs at the interfaces between the perovskite and the transport layers. So we were adding in some thin passivation layers to improve the quality of the solar cell. So what we used was a mixture of PMMA and PCBM. Now, PMMA is an insulator and PCBM is an electron conductor. And what we found was that having a mixture of the two gave us the best combination of passivation and electron conduction. So if you just had PMMA, you could get a high voltage, but in that case, the fill factor was quite low because it wasn't conducting so well. Whereas if you just had the PCBM, your fill factor was high, but then your voltage was low. By having the combination, we could improve the trade-off and lead to a higher efficiency overall. So this is some of the early work. We then applied passivation to both sides of the solar cell, and that was a high voltage that we achieved at that time. We did some characterization and computation and by FTIR and NMR and DFT, and we found that the PMMA actually passivates defects on the perovskite surface. And this was important because it's a universal approach, so it works for a range of different perovskite compositions. So having that PMMA passivation layer is very useful because often you're changing the perovskite composition, for example, to tune the band gap of the solar cell. Moving on from there, we've tried other approaches to passivation, and in this case, we used titanium dioxide nanorods for passivation. And we coated the nanorods with the PMMA PCBM passivation layer. And what we found there was that we were able to get a particularly high fill factor by using the nanorods. So you can see comparing the planar cases with the nanorods, you have a very much higher fill factor. And so this was that at the time, that was the highest efficiency for a 1 square centimeter cell. And when we looked at what was causing this high fill factor, we found that we did some simulations where we simulated the nanorods as partly coated with the passivation layer and partly bare. And we found that we needed to do that in order to understand what was happening. So what you get then is a local passivation effect. You're passivating the bottom of that nanorod layer, but the tops of the nanorods are bare, and that allows better conduction to the nanorods. And so overall, by doing that, you're able to get a higher fill factor. So we then did some related work using a mixture of 3D and 2D perovskites. And this is interesting because it was quite a different approach, but in the end, the mechanism is quite similar. So here we've got a mixture of butyl ammonium iodide and 2D and 3D perovskite passivation layer. And what we find is we get an increased fill factor and efficiency. And we find that the 2D coated areas give you effective local chemical passivation, but of course they don't conduct so well. But you also have the 3D area, 3D film, which is partly exposed, providing the conductive pathway. So what you can see that's in common with several of these studies is that you have a lot of the area that's covered with film that's not very conducting, and that improves the voltage. But there are regions that are exposed and give you better conduction, and that way you can get both good fill factor and good voltage. And in fact, this is the same physical principle as the PERC silicon solar cells. So those silicon solar cells, you have a completely different scale, which they're talking about hundreds of microns instead of hundreds of nanometers. But the physical principle is the same. You want to have most of the area passivated and only some areas exposed, allowing that conduction. So recently we've looked at changing the electron transport layers. And one of the typical electron transport layers is titanium dioxide. And we've modified that to create a titanium oxynitride. One of the limitations of the titanium dioxide is its conduction is not as high as it could be. So titanium nitride, of course, itself is very conducting, but also not transparent. So by using titanium oxynitride, you can get a film that's highly transparent, but also highly conducting by getting that mixture and also by treating it at around 450 degrees. Now, the interesting thing with this device, again, we were able to get very high fill factor. So this was over 86% fill factor, 22.6% efficiency for a 1 square centimeter cell, which was the highest at that time. And what you find here is quite counterintuitive, is that the conductivity of the electron transport layer is actually different when it's inside the device and to when it's outside the device. This is something that was initially very surprising. But what's happened when it's inside the device, you actually get depletion of the electron transport layer due to band bending when all the layers line up together. And so you have a depleted number of electrons in the electron transport layer. So it effectively has low doping when it's inside the device, and that means it's much more resistive than you expect. But by going to titanium oxynitride, we overcome that issue, and therefore we're able to have a much higher fill factor. All right, so that was our work on improving the efficiency of single junction perovskite cells. I'll now tell you a bit about our work on tandem devices. So with tandem devices, there are two main types of tandems, 2-terminal and 4-terminal tandems. So in a 2-terminal tandem, you have the perovskite and silicon directly connected together, and you just have the two wires coming out of the device. In a 4-terminal device, you have the two cells constructed separately and then mechanically stacked. So that's the difference between the two structures. And we've been doing work on both of these structures. But I'll describe first our work on the 2-terminal devices. So this is some of our first work on 2-terminal tandems a few years ago. We created a new design that doesn't require an interconnection layer. So normally you need an interconnection layer between the silicon cell and the perovskite cell, which is often a transparent conducting oxide layer, for example, which does introduce extra optical losses. So we remove that to have direct connection between the titanium oxide and the P+ polysilicon of the silicon cell. And overall, we're able to achieve 24% efficiency for that 2-terminal tandem. The interesting thing here was the mechanism and actually what was happening, which is again quite surprising. And we did some test structures to understand what was going on, because what we had was titanium dioxide directly connected to P-type silicon. Now, titanium dioxide is N-type, P-type silicon is obviously P-type. So you would expect to create a diode there. You would expect a Schottky junction. And indeed, we found that was the case sometimes when we deposited titanium dioxide by some methods. But when we deposited by other methods, we actually got an ohmic contact, and the type of contact depended on the deposition and annealing conditions. We also did some simulations to understand what was going on, and we found that what can happen is that depending on the band offset, that delta there, capital delta, if that is about in the right size, you can actually get tunneling of electrons and holes to interface states at the interface between the titanium dioxide and silicon. And so you can get recombination exactly at the junction. So rather than having to add an extra recombination layer, you can actually get recombination directly at the interface and avoid those extra losses with that layer. More recently, we've been doing some work on TOPCon silicon cells. Now, TOPCon cells are important because they're one of the types of cells that's currently being made in industry, and they're high efficiency standard industrial cells. So we were looking at how we could put perovskite cells on top of these TOPCon silicon solar cells. One of the key things that we had to overcome was the rough surface of the silicon solar cell. Now, a silicon solar cell in industry will always be rough. Most people, when they're making cells in the lab, will use a polished silicon wafer, and they'll use a polished silicon cell. But that's just completely impossible in industry. It's very expensive to polish silicon. So usually in industry, they will have a textured surface, but it will at the very least be saw damaged. And so there will be features on the surface of the order of a micron or so. So we needed to figure out how we could manage those losses. So we worked out ways to mitigate that rough surface and also other ways to deal with reflection. Some of the key things that we found were necessary were to avoid the shunting, were a dense nickel oxide hole transport layer, a passivation layer with high molecular weight, so it's covered the surface really well, better uniformity of the perovskite using the vacuum flash method, and dense tin oxide electron transport layer. So overall, putting a lot of effort into making sure that all our layers were dense and highly uniform. And by doing that, overall, we're able to achieve a 27.6% efficiency perovskite tandem on an industrial compatible TOPCon cell. All right, so I'll move on now to the 4-terminal tandem work that we've done. So in a 4-terminal tandem, where we're mechanically stacking the perovskite cell on top of the silicon solar cell. So the work that we've done here involved increasing the quality of the perovskite layer. In this case, we're working on bulk passivation, so improving the quality of the perovskite itself. And what we found is that adding methyl phenyl ethyl ammonium chloride actually enhanced the bulk quality by suppressing the defects. You can see these in these thermally induced current measurements. By changing the temperature and looking at current passed through a device, you can get a measure of the number of traps. So adding the passivation material significantly decreased the number of traps. You can also see that on the right-hand side in the minority carrier lifetimes, the photoluminescence decay. So the photoluminescence decay happens much more slowly for the target device, indicating better electronic quality. And finally, in the bottom images, you can see that's photoluminescence steady state intensity, and you can see a much higher photoluminescence intensity, again, indicating better bulk quality. So we put those perovskite cells on top of silicon solar cells, and overall we're able to get an efficiency of over 30% by having the perovskite solar cell with improved bulk quality on top of a high efficiency silicon solar cell. Now, I've talked about cost and efficiency, but lifetime of the device is also really important. Overall, all of these lead to cost, but what we're looking for is low levelized cost of efficiency. So we're looking at for low cost of electricity over the lifetime of the solar cell. And in order to do that, you need low cost per watt, you need high efficiency, and you need a long lifetime of your solar panel. This is certainly a challenge for perovskites. There's a long way to go here. We need to overcome a number of different degradation mechanisms, including moisture, light, high temperature, and electric fields. All of these tend to degrade the halide perovskite materials. And we've written a review paper this year, which focuses specifically on degradation mechanisms for tandems. Just to give you an idea of how much needs to be done, there's much less work that's been done on perovskite silicon tandems than on single junction perovskites. So you can see on the left-hand graph here, the red dots there are the tandem devices, and you can see that most of the measurements have been relatively short for tandem devices compared with single junction devices. There's just been much less work done. And similarly, on the right-hand side, there's been very few measurements over 1,000 hours. And so we just don't know what can be achieved with perovskite tandems. So there's very much work to be done. And there's also a lot of potential degradation mechanisms. So there's a lot to be studied about the different ways that they can degrade and how we can overcome that. So this isn't a comprehensive review. I'm just going to point to a few of the mechanisms here. One of the mechanisms is the strain in the perovskite. So you form the perovskite usually at a temperature of 100 or so degrees, and then it cools, of course, and you have a thermal expansion mismatch with your substrate. And you can see on the graphs at the bottom left there that there is a big mismatch, especially between whole transport layers and other materials, but also between all the different parts of the device. And so this is something that's going to lead to strain in the device and potentially degradation. Another key issue is diffusion. So with perovskites, you really have to think of what we're doing here as solid state chemistry, because things are moving all the time. Even at room temperature, there can be diffusion, but particularly in elevated temperatures, such as you might get when you have a solar panel on your roof. You'd be typically looking at a temperature of 60 degrees or so. You'll get metal diffusion into the perovskite. You can get the ions diffusing. Things can move around everywhere, and all of this needs to be taken account of. And sometimes you need to put layers in there to stop that diffusion. So these things can all lead to degradation. So these are degradation mechanisms at the cell level. Now, there are also extra degradation mechanisms at the module level. I'll just give you a few examples of that. So one of them is that when you have a module, if you partially shade the module, some of the cells will be in reverse bias. Now, if you have some of these cells in reverse bias, and especially if the cell is non-uniform, then you're going to tend to create hotspots within the cell. So some of these spots can get so hot they can actually be hotter than the degradation temperature of the perovskite. So you could get to 120 degrees or so. The perovskite may break down. So that's so reverse bias is a significant issue for perovskites. Another potential issue is potential induced degradation. Now, this is also an issue for silicon solar cells, actually. When you have a string of modules, you can have around 500 volts between that module and the ground. And the result of that is that sodium ions in the glass can actually move. And of course, for a perovskite, ions within the perovskite could move as well. So that would be expected to be worse for perovskite tandem modules. You can also get layers peeling off. They sometimes don't actually adhere very strongly to the perovskite. And in particular with thermal cycling, I said we have the thermal mismatch between the layers. So the thermal cycling will tend to exacerbate that and tend to lead to layers peeling off or to layers actually cracking under load. So all of these things are things that we need to figure out, and we're really only in relatively early stages of doing that. All right, to get towards the end, I want to go back to hydrogen and talk about what we could do to make renewable hydrogen and how that would relate to perovskite tandems in particular. So I've said that if we can decrease the cost of solar, then producing hydrogen from electricity could potentially become viable. So for producing hydrogen, you can do this in a few different ways. You can connect your photovoltaics directly in an electrolyte and have a kind of photoelectrochemical system, or you could have a photovoltaic electrolyzer tandem when you just use the solar cell and you connect it to an anode and cathode that are covered with catalysts, and they're in contact with the electrolyte. So there's a range of different ways of doing that. But just the same as for solar photovoltaics, you want to get a high efficiency in order to have low balance of systems costs. So you need high efficiency if you want to have low cost overall. So tandem with perovskites are particularly attractive because you get an extra voltage. They're a high voltage design. So a silicon solar cell is only going to give you around 650 millivolts, something like that. For solar water splitting, there's a theoretical minimum of 1.23 volts, and then you need a few extra 100 millielectron volts to take account of the overpotential. So by adding perovskite photovoltaics, you have extra voltage, and so with that, you can potentially get a high efficiency system with standalone water splitting. You don't have to add any extra voltage. So that's something we've been working on. We achieved over 17% standalone water splitting in 2020. So using a silicon photocathode connected to an electrolyte in that case, and adding a perovskite cell to increase the voltage. More recently, we've used the perovskite and silicon tandems, this time in an photovoltaic electrolyzer tandem configuration, so keeping them separate from the electrolyzer. And in this case, we also added low-cost catalysts. So these are nickel iron, nickel molybdenum catalysts, so avoiding any noble metals in order to reduce the cost of the whole system. And overall, we were able to get 20% solar to hydrogen using a low-cost approach. And that's very important, again, for reducing the cost of the whole system. Okay, so just to conclude, we've got more solar being installed annually than any other energy technology. This is important for electricity. It's going to be the most significant source of electricity globally, certainly. But also cost reductions means that there'll be new opportunities for solar to produce hydrogen, for example. Perovskites provide the opportunity for high efficiency and cost reductions for solar cells. We can also use them to make high efficiency tandems for water splitting. So overall, a very highly prospective technology. But as I said, there's still plenty to do in terms of further increasing the efficiency, in terms of scale up, and also getting the high stability that we really need for commercialization. And with that, I'd just like to thank everybody that contributed to this work. These things are always a group effort, of course. All right, thank you.
Thank you very much, Kylie, for very impressive achievement and also very nice talk. Now let me to introduce our panelists tonight. Firstly, we have Dr. Annalisa Bruno from the Nanyang Technological University. A brief introduction for Dr. Bruno. Dr. Bruno received her BSMS and PhD degree in physics from the University of Naples Federico II, Italy, where she worked as also postdoc in the physics and chemical engineering departments. Then she joined the chemistry department of Imperial College London, first as a postdoc research associate, studying organic and hybrid materials for optoelectronic applications. And then in 2011, she became a senior staff scientist at Italy National Agency for New Technologies, Energies and Sustainable Economic Development, and a long-term visiting staff Imperial College London. In 2014, she joined the Energy Research Institute at Nanyang Technological University as a senior scientist, leading the thermally evaporated and tandem solar cell team there, aiming at developing highly efficient large area solar cells. Our second panelist, Professor Fan Wang from Beihang University. Unfortunately, due to the last-minute travel delay, he couldn't actually join us tonight. So instead, we're able to find Dr. Chao Hao Chen, who we don't have time to put his photo here, but you will see him on Zoom, where he going to replace Professor Fan Wang as our panelist. A brief introduction of him. Dr. Chao Hao Chen obtained his PhD in physics from the University of Technology, Sydney in 2020. He's currently employed as a postdoc researcher at the Photonic Labs in UTS Technology Labs, where he leads the direction of research in nanophotonics. His work is focused on developing techniques for the optical characterization of nanomaterials and super-resolution imaging. Dr. Chen has published as first or corresponding author in many renowned international journals, including Nature Photonics, Nature Communications, Light Advanced Materials, Nanoletters, and Advanced Sciences. Our ex-challenger tonight is Zhongyang Ren from Peking University. Zhongyang received his bachelor degree from Fuzhou University in 2017. He's currently doing PhD at the National Key Laboratory of Nano Microfabrication Technology, School of Integrated Circuits, Peking University. His research focused on energy and nanoelectronics. He has published many papers, including Nano Energy, Applied Physics Letters, and others. He received the Best Poster Award in Microsystems and Nanoengineering Summit 2019, Excellent Master Dissertation of Fujian Province in 2021, Outstanding Scientific Research Award in 2022 by Peking University, and various other awards. So now let's welcome our panelists tonight. On the stage, please. All right. As usual, we're always starting from our ex-challenger. So, Zhongyang, please go ahead with your questions.
Thanks for the introduction and Professor Kylie for the excellent presentation. Through material and structure improvement, you have effectively enhanced the stability and efficiency of perovskite and silicon tandem solar cells. So I have two questions for application standpoint. First, the effective area of the solar cells is crucial to its power generation. But a large effective area can impact the efficiency. So how can we balance the relationship between effective area and efficiency? The second, a large effective area also means increased difficulty in device packaging and reduce stability. So how can we balance the relationship between the effective area and the device stability?
Okay, yeah, thank you
So
for the
it's my question.
Yeah, thank you for the question, Songyang. I'm going to give my answer, and then I'm going to ask Annalisa to add some extra, because this is particularly her area in talking about how you go to large area and how do you go to modules. So there's a range of things that you need to consider. You need to think about what kinds of techniques that can give you good uniformity. And you also need to have device designs that especially reduce the series resistance losses. So this is a big problem. Certainly things like organic solar cells have found it very difficult to scale up. And you'll see also for perovskite cells that there is quite a decrease in efficiency as you increase the area. So having designs for modules where you have very thin strips of cells is helpful, because then the individual cell does not have to be too wide. But then you also have to have a way of packing the cells so that the area between the cells is small, otherwise the efficiency will also be low. And then you need that uniformity also. You need that, I think that's a matter of designing the fabrication processes, and also maybe going to somewhat thicker cells, and then also improving the bulk quality so that we can avoid some of those losses. Now I'm going to pass to Annalisa to answer more of this question, because it's quite a broad question.
Yes, thank you very much. Thank you very much for the questions and for passing the word to you. I completely agree on what you already said, that is indeed to scale up, we need to really work on two main areas. One is guarantee the uniformity, of course, of the perovskite, but also on the other layers over a large area. So we really need to think in terms of scalability of the processes that for the perovskite, but for each of the interlayers, because each point of defects can be a defect through the whole devices. So the chances are very high. And for example, beside the deposition techniques that we use and the quality of the film is also the cleanness of the environment that we use, because very small particles can be also the sources of shunted or of extra defects that usually on the small areas, this is a kind of problem that we don't deal with, because it's a question of statistics. The chances that you got some particles in the small area are much lower. So this is on the uniformity of each layer that is very important. And this is a challenge for the perovskite technologies, because very good technique that work very nicely on the small area. When they scale up, they cannot maintain the same uniformity in terms of composition, in terms of morphology, and in terms of also of thickness over large area. The second point is the actually design of the devices, because as Kylie said before, the minimizing the sheet resistance is very important, but it's also design the sides of the small of the subcells in conformity also to the dead area that we require. So, for example, we have been doing some work in this regard, and we have seen that where we use different methods to create different dead areas, the dead areas is basically the distance, is the area that we are not going to use in the cells. It means it's the area that's is between the two subcells. Regarding also the size, the dimension of this dead area needs to be taken into account, because different dead area requires also different size of the subcells to have a power optimization of the old devices. So these are the two main challenges. So the device structure and the device design in order to scale up. course, this comes also with increased degradation that we can have on the large area, because the point of access of external elements such as water or in general moisture, and also they are extended. So it's something that we also need to look into. And then, of course, we still need to look into a proper encapsulation when it goes also on the large area. I think this is the a large.
Yes, thank you.
We still have a lot of work.
We still have a lot of work.
Yeah, I can see that. So Zhongyang, do you have another question, or is all your both questions being answered?
No other is my question. Okay.
Okay, so then maybe Annalisa, you can keep going. Do you have any question to Kylie?
Yes, I really like your talk, and it was very inspiring, like usual. And mostly I was very much curious regarding the passivation strategies that you had with the PMMM and C60 on top. I saw, and then with C60 below, and on top it was just PMM, right? So my question is, how do you control really the morphology of the below layer in order to keep a good morphology of the perovskite? Is this represent a challenge for you?
So we had on the bottom we had PMMA and PCBM.
Mm-hmm.
These layers they're very, very thin, only around 5 nanometers, something like that, spin coated, and well, we found that didn't cause problems with the morphology of the perovskite. In terms of actually kind of figuring out what was actually there in the layer is very difficult. Of course, you can't see it even with TEM. We tried, so it's hard to tell, how much of the layer is coated with PMMA and PCBM, but you have some sort of mixture. So what we were finding, I guess, that of course these sort of thicknesses you don't have. You must have some areas of one material and some areas that just because of the thickness of the material, but we couldn't see it directly.
Okay. But you didn't find that the morphology changes in a way when you grow the perovskite on top, because this is one usually of the problem that we have a lot with the co-evaporation.
There are some materials where we've had wetting issues and things like that, but in that case, no, we were able to grow the perovskite well. Yeah.
Okay. And the other question regarding the structure that you had with the pillar in the ITO. So my question is, how did you create the passivation that it doesn't stuck? I mean, how do you control that the passivation just stays on the bottom, and do you really separate it with the rods? That was impressive.
Well, so no, I mean that is self-assembled, I guess, because we spin coated the PMMA PCBM on top of the nanorods, and then we tried to figure out what was happening, because if you just do the simulations assuming that it's fully coated, then you don't get an increase in fill factor. So we were trying to figure out where can the increase in fill factor come from, and according from the simulations, the place it can come from is if the top of the nanorods is not coated, and that makes physical sense. I guess that would be the hardest place for it to coat.
Just to stick.
Yeah,
the problem of sticking.
But it wasn't controllable in the sense we couldn't decide how much of the nanorods that we would coat, though. Yeah.
But from the simulation you can estimate, because the agreement was impressive.
That's right. From the simulation you can estimate how much must be coated. That's right. Yeah.
Yeah, this is counterintuitive in a way. It was not the first thing I will have think of. That he behaved
No.
like this. Yeah.
No, it wasn't the first thing that we thought of either. And it was, I said that we found several different ways of getting high fill factor through using an area that was mostly passivating and with a few conducting layers, and that wasn't exactly a deliberate strategy either. We were trying a few different things, and we noted that the same thing was happening with these different approaches, and then realized this is the same thing that happens also in silicon solar cells. They have the same physical mechanism. Yeah.
Okay. Thank you. Now, Chao, do you have any questions?
Yes. Hi. Okay, thanks for your nice talk. Actually, I have two or three questions here. The first one is like in your recent publication, you achieved a record fill factor over I think it's 86% in solar cells by using the low temperature solution based deposition technique. So I just a simple question is like, could you please discuss how it compares to the commonly used techniques such as spin coating or vapor coatings or vapor depositions techniques?
So the 86% fill factor was with the titanium oxynitride. So that's a different electron transport layer. So that was sputtered and then annealed. So we did sputter coating of titanium nitride, and then carefully annealed in oxygen to introduce some oxygen into it. So having that careful control was important. In terms of the different ways that you can produce the layers, sometimes people use ALD for titanium oxide or tin oxide. So ALD, I mean, it's nice in the lab, but it's a pretty expensive sort of process overall. Certainly, and the ALD titanium oxide is not really conductive enough. Other techniques you can use tin oxide nanoparticles, so you can use these sorts of approaches as well. I mean, sputtering is really nice as a industrial type process. This is a sort of I don't know if people these days like, oh yeah, chip packets, crisp, like potato chips. They sputter the metal onto the plastic, right? So it must be an extremely cheap technique. So sputtering is nice from an industry perspective. You would have to have that careful control of the annealing to get the titanium oxynitride, but I mean, the titanium oxynitride seems like a nice material in terms of both conductivity and transparency. So it's can be a little bit difficult to work with, but so can tin oxide, I have to say, having spent quite some time getting tin oxide cells working in our lab. So it's hard to say, and the listeners what I'm talking about. Yeah, so it's hard to say what would be better from an industry perspective. Yeah.
Okay, thanks for your explanation. My second question is like it's just a common question. It seems that perovskite and silicon-based tandem solar cells hold a great potential for achieving a higher efficiency. So I think you also have introduced their current commercialization status. So may I know what's the major challenge finding their larger scales commercial productions? I know maybe it should be like stabilities or durabilities or like manufacturing cost. So could you please introduce more information about it?
Okay. Yeah. So what are the major challenges to commercialization? The cost seems like it will be okay. I collaborated on a paper looking at the cost of perovskite silicon tandems, and it looked like it's in the right sort of range. There are different types of structures that you can make. Obviously, you have to get rid of a number of things that we often use in the lab, like gold and spiro, which are way too expensive. But there's certainly ways of doing that, and copper looks very promising as a metal for perovskites. Once you get rid of the sort of obvious expensive materials, then the costs look reasonable in terms of materials and also in terms of production methods. So the efficiencies are now getting, I mean, we're looking at sort of 30%-ish on a cell level, small cell level, but we really have to be getting that more like on a module level to be worthwhile. When you think silicon, the best silicon cells are 26%. The silicon modules are not far behind. So if you want to have something that's, you obviously have extra cost in adding the perovskite cell on top. So you really want your module to be at the 30% or so level, which means that your cells should probably be 35, really. So I think we've still got some way to go with the cells themselves. Then there's the scale up. There hasn't been, I think, that much work done on the scale up. The efficiencies are lower, but I don't really see fundamental reasons why they should stay lower with sufficient effort in that direction. The thing that seems to really need plenty of work is the stability, of course, and you have to have some kind of product that's compatible with a silicon module, right? If you're going to make a tandem, your silicon cell is going to last for 30 years. You don't really be wanting to sell something which is only going to last 10 years to put on top of that. So I think that's really the thing that needs a lot of work still. There's been good progress using the formalinium-based perovskites, showing more stability, but the other layers in there need a lot of work there as well. So, and you saw on the graphs I was showing that there just hasn't even been the testing beyond about 1,000 hours. People do that as a standard, but that's going to be, I think, the thing that needs a lot more effort and maybe some more standard tests. We did some work a few years ago which showed that the results of light and heat separately were different to light and heat together for perovskite cells, which was kind of surprising. But we ended up with, when we had light and heat together, we had gold migration, which wasn't happening when they were applied separately. So there may be some kind of extra standards that we need for perovskite cells. One of the things that I'm seeing in the journals that's good now is that they're asking for a certain set of standard tests to be passed, to be asked to show stability under light or under bias, under heat, to actually report things in the same way. Whereas so far, people have just been reporting stability any way they wanted to. So having that standardization, I think, will help a lot in being able to figure out just where we're up to in terms of stability, and to be able to assess, which approach is better than others. So I think things are moving in the right direction there, but there's still quite a long way to go. In terms of industry is, there are some sort of early adopter firms that are pushing ahead with perovskites, but there's also a number of big companies that are sitting and waiting. On the other hand, they have the motivation to have new technologies. They want to have something that moves beyond silicon as well. So it's, at a certain point, they will probably jump into it and start putting more investment into it, but it's hard to say when that might be.
Yeah. Okay. Thanks. Oh, my last question is like in terms of the energy storage efficiency and the cost effectiveness. So I'd like to know your opinion about how does the electricity generation from the renewable sources compared to this kind of novel approach generating both electricity and hydrogens as in your talk.
Sorry, how does what compare?
How does the traditional electricity generations from the renewable source like the wind or some things compared to this solar cells generate both electricity and hydrogens at the same time?
Okay, so you wouldn't produce electricity the solar cells that I was explaining, they were producing, it was a way to produce hydrogen. In general, I think the reason that you would use hydrogen is if you want hydrogen for something, if you have an application where it's hard to use electricity. So it is possible to produce electricity and then produce hydrogen and then use it to produce electricity again, but that's really inefficient. It's so you would lose a lot of energy. You use like 3/4 of the energy doing that. So in general, if you want electricity, you produce it directly from a solar cell. But in some cases, you want high temperature heat, like 1,000 degrees. That's hard to get with electricity. Or you want to produce iron from iron ore. And in that case, you need actually something that can chemically reduce the iron ore. So hydrogen is good for that as well. So what I'm proposing hydrogen for is not cases where you would normally use electricity. In that case, you'd be better off just use a solar cell. It's only if you need the hydrogen for something else. Yeah.
Okay. Thanks. Yeah.
Okay, so Kylie, you've got you've been very well known for your expertise in your light management using photonic structure design and all this. So will that be able to? And of course, you show a little bit about using the nanorods to enhance the efficiency. But for the tandem cell, will that be any type of light management sort of design helpful?
You definitely need some kind of light management. Whether it's nanophotonic or not is an open question. But the reflection losses are quite severe for tandem solar cells. If you look at all the interfaces you have quite some refractive index mismatches, and some of them are hard to deal with in the perovskite cell. You have some layers which have quite different refractive indices because you need them. Electronically, it's hard to do anything about those index mismatches. So you have to figure out what else you can do. A nice thing to do is to make your perovskite cell on a textured silicon solar cell. That's nice because if it's on a textured silicon solar cell, then the light can bounce and hit the perovskite and bounce off and hit the perovskite again and have another chance of getting in there. Of course, if you do that, then you have to make a perovskite on a textured silicon solar cell, and that's not easy to do. Certainly, it doesn't really work if you try spin coating it. So you have to look at other methods, for example, evaporating at least some of the layers. So that's certainly been done, but it's hard to get the electronic quality as good. You do tend to sort of get gaps and things like that. Certainly some groups have got high efficiency that way. There's also been some work done using silicon nanotextures, so putting your perovskite cell onto a silicon nanotexture. So then that's kind of appealing as well. And there's other things you can do, like reduce the reflection from the top encapsulation layer as well. It's quite common to make molds out of silicon cells, actually, so you have a silicone type mold, and you can have a texture on that and reduce the reflection. So overall, I guess there's many things to do to reduce those reflection losses, particularly. So it's a different challenge from previously with when we were making thin silicon cells. The challenge is silicon is an indirect semiconductor, of course, so it doesn't absorb the light very well. So you had to make it bounce back and forth inside the cell. The perovskites are direct semiconductors, so just a few hundred nanometers will do to absorb the light. But you do have those reflection losses everywhere. And they're one of the biggest loss mechanisms, actually. It's where you're losing a lot of the current. So that's something that really does need to be addressed better.
Sounds interesting. Also from, the plot, you showed to make this hydrogen generation viable, you actually need to get quite high efficiency from the, PV cells. So is this two tandem enough? Like you do show they're quite good if it, like the theoretical is 47 or something %, right? That certainly entered a range of sort of viable range, but to reach that looks like still a long way to go. So are there any other strategies in addition to two cell tandem? Are there any, like 3 cell, would that be more easy? Of course, that's challenging to do multi-cell, but 3.5s, they do four tandem now. So how is the progress in 3 cell tandem or other alternative sort of approach?
For the graph for the solar hydrogen, I was showing that was the electrolyzer efficiency. So they're already in the 50 to 70% range. So that's okay. It's true, though, that there's going to be a constant drive to increase the efficiency. This won't go away. We'll want to be continuing to reduce the cost of solar, and so there will be a continuing pressure to keep increasing the efficiency, especially as it becomes the world's major energy technology. So I think the same thing will happen as in the 3.5s, that you'll go to multi-junctions. Why not? With the perovskites, that would mean putting 2 perovskites on top of silicon, for example. So you can certainly do that, and people are already making all perovskite tandems. So you can put a perovskite on top of a perovskite, different band gaps. You get lots of extra challenges, of course, especially if you're trying to solution process, because then you try not to dissolve the first perovskite as you deposit the second perovskite. So in general, the perovskites, they're quite soft, easily degraded materials. The processing that happens normally at around 110 degrees or so. If you're going to be applying those kinds of temperatures to your previous perovskite, then there's potential to degrade them as well. So I would imagine you tend to go to more evaporation type methods in order to do that. Evaporation is normally a nice gentle thing to do. But there's lots of scope to do that, and I think there will be a continuing drive in that direction. Just also from the point of view of cost, right? To especially if you're doing something like an evaporation that you could do multiple steps in one batch, then you may as well make a couple of cells rather than one cell. It probably wouldn't be that much extra cost. Well, that said, we have found that the number of steps in a process is one of the things that drives cost. So it's not just the materials cost. So there will be some kind of balance still. I think there would be that ongoing drive for efficiency. So we'd be certainly wanting to look at the 3-terminal tandems probably in the relatively near future.
Great, thank you. Annalisa, I think you.
This is. Thank you very much. I wanted to add something. This is a very interesting topic for me, and then I was really, when Kylie, you showed the time of production of the cells, right? The silicon solar cells is 1 cell per second. I think it's also where something where perovskite really need to catch up, because now everything is slow. So what do you think? Thermal evaporation, it can be a very nice process and on the interlayers, but beside everything is the whole processing time that is also something that we need to really look this in the future, to really need to look into, to make it to look at the next step for perovskite, to make it suitable for commercialization, but also really to production. Is still something that in a way worries me a lot because the extended time of production for one cell, the number of process with the whole time, it makes exploding the cost that in principle can be instead reduced. So
yeah, that's
one
a
more
very
thing
good
to look at for us.
That's a very good point in the terms of the different techniques that we look at. What we can do in the lab is different from what's feasible in industry.
So just talking about the commercialization, and you mentioned there's a lot of interest, also a lot of leading groups and companies doing that or waiting for the technology. Are there any actually commercialization, product available now on the market? I haven't really follow up that.
Not available to my knowledge. The furthest ahead is Oxford PV, and they've been doing field trials. So they're making modules and putting them in field trials. There are other companies who are making modules, but I think at the stage of doing extended testing rather than being available on the market.
Right. Okay, so
I also know about Seoul that is doing some shading instead of doing the full modules, so on a smaller scales, to do shading for the building. So something very light, plastic that can be used like a shelter, then, but not as commercial available. But I know that it's doing extending testing, as Kylie was saying, but also not aware of.
Right.
Yeah.
There's certainly a lot of space to push forward. Yes. We do have time for a very last question. So anyone wants to ask the last question? Okay, if you don't have, I do have a question to ask Kylie. It's probably about a very general question. Perovskite is certainly very highly competitive field. There's so many interests and from everywhere. So Kylie, what do you feel when you're moving from silicon, to, of course, you're still using silicon to perovskite, but totally, moving to a new sort of field with organic components there. So how do you feel, like really sort of changing a gear a little bit? And
I felt completely daunted. It was a very new field for us. We were a silicon group. We hadn't done anything with any organic materials, anything like that. We didn't have a glove box to start out with. We did our fabrications in a plastic bag, a nitrogen-filled plastic bag to start off with. We had efficiencies of 5%. And then we had a home-built glove box and got efficiencies about 12%. And then we finally bought a glove box. So it was a big learning curve for us. I guess in terms of advice for people, I would say, firstly, be strategic. So the key thing that I thought, there's two key thoughts. One is that silicon based tandems would be a big thing because silicon is so big. And so that there would be a push from industry actually to have tandems on silicon, because the silicon industry has so much money. And so it's attractive for them. If you can put a cell on top, then they have a premium product. If they have a premium product, they can sell it for more, right? Whereas otherwise, if you just make a perovskite cell, then you have something that's not more efficient, and you're making it in much less volume, so it can't compete. So the things I thought was that silicon-based tandems could be competitive because you in the initial stages, you could have something you could sell at a higher price, and that would allow the price to come down. The other thing I thought was, as a silicon group, we had a strategic advantage to work in silicon-based tandems. So that was sort of both a push and a pull in terms of where we were working and in terms of what I thought a good long-term direction was. So I think thinking about that fit between what you're doing and where you think things will go is really important in terms of figuring out what's a good direction to go in.
Excellent. Thank you so much, Kylie. And also thank you very much for the panel, for a great discussion tonight. I think that's what we have all the time for tonight. So now let me just go back to Kay. So representing ICANX, here, Kylie, I just present you the certificate, which will be delivered to your mailbox tonight for the acknowledgement from ICANX for your excellent talk and contribution to our series. So for next Friday, again, we'll have the Young Scientist Awardees to presenting us. So there'll be 2 speakers to present at ICANX talks next week. That's all for tonight. So thank you very much, everyone, for joining us. See you next time.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤。